So it's my great pleasure today to introduce Rick Cory. Rick's done some fantastic work on perching aircraft. You'll see a lot of the work he's done in his talk, but what you won't see is all the other sort of amazing things that Rick's done over his time here. So, I mean, just last weekend or 2 weekends ago, he was at the Museum of Science helping kids build ornithopters and throwing them around. He's been an absolute inspiration to all of us in the group. I count my blessings that he even decided to work with us in the first place, because we like to joke. He first came to me saying, I'm probably going to come to MIT, I'm looking for people to work with. I was actually still a student at the time, so I wined and dined him at the food trucks, right? And we had a nice conversation on the bench out there, right? I didn't have a lab or anything, so he took a chance on me, and I'm very happy that he did. He took a chance on flight, and I'm very happy that he did. And I'm very, very happy that he's here defending today. So take it away, Rick.
Thanks. So yeah, back in 2005 when I joined Russ's lab, he had actually just finished his work on a little walking robot named Toddler, 2 legs, learn how to walk. So we were pretty inspired by that. So we said, so what problem can we sort of look at that would really push the limits of the control system? And we said, well, if we can make a robot learn how to walk, can we build a robot that can learn to be as graceful and fly like a real bird? And I was like, that sounds awesome. I'm in. And so it turns out it's a tough problem, of course. But one of the toughest problems is actually getting the right experiment to really understand sort of the fundamentals of agile maneuvering flight. And so, after doing a lot of field work, namely watching birds, on the beach or whatnot, we sort of became enamored with this one maneuver, really beautiful maneuver that really we felt captured a lot of the characteristics that are sort of fundamental of these aerobatic maneuvers that are pretty pervasive across the library of stunts that are executed by birds, and that's landing on a perch. So 5 years later, we fast forward. I'm going to show you this high-speed video, and what you're going to see is you're going to see a glider being launched from the right-hand side of the screen. It has no propeller. There's a single motor at the tail controlling the tail. It's computer controlled. It's coming in at about 16 miles an hour. There's a suspended string about 12 feet away. The idea is that this glider has to land on that string, minimizing the amount of speed that it has at landing. And it has to happen in a fraction of a second. So it gets launched. The computer's controlling the tail, kicks it up to a high angle of attack. See this little hook here? That's the one that has to land on that string there. It's coming up sort of stalled already and sort of makes that point landing. So for the rest of the talk, I'm going to tell you exactly how we did that. But that's sort of the motivator. So before you do that, I sort of want to make sure that everybody understands what I mean by supermaneuverability. And what I mean by that is, so if you look at the literatures, you scour the literature, you come up with a definition that's something similar to this. And that's saying that it's a threshold of maneuverability that's beyond the limit of that's supported by conventional aerodynamic control. Conventional control here means what you can do with standard control surfaces like elevators, rudders, and that kind of thing. But it's still quite vague. There's really no quantifiable metric that tells you that an aircraft is super maneuverable. So what's the next step? We start looking at some videos of what these aircraft can do, these super maneuverable aircraft, and we can sort of at least get a sense of, this should play.
It's playing up there.
Oh, is it?
Yeah. There's just no audio.
So this is a Su-30 Russian fighter. You can use it to do some pretty amazing things. So there's a human pilot in there, pretty skilled obviously, doing 360s in midair. At this point, he sort of starts flying backwards. Starts almost tumbling down to the ground like a leaf. And so he catches himself and gets ready to execute the next one. Just very similar to sort of stop almost in midair. And come back down, catch yourself, and he's going to get ready to execute the next one.
We can't hear you over the engines.
Yeah, the engines are pretty bad. So the point is here, that's extremely impressive. Right? Even if you didn't hear me say anything. So the question is, what's left? It seems like we can do some pretty amazing things even compared to birds. So what exactly is left? Well, one of the things is taking the pilot out of the loop. But even then, there's a big challenge that these control systems really don't address, and that's being able to be accurate
Jay and Megan, they've never landed a Tomcat on the aircraft carrier. You know, it's daunting. It's a 64-foot wingspan. The landing area is just a little bit wider than the wings on either side. You know, the margin for error is measured in inches. There's planes parked on the right side. There's people in planes on the left side. If you're off center line, you're going to hit somebody. If you land too long, you're going to miss all the wires and you have to go around.
Wave off, wave off. Burn.
If you land too short, you scare the hell out of everybody, and there's a decent chance that you're going to slap into what's called the round down, the back end of the boat. So basically, you have to take the hook point that hangs behind the Tomcat. You have to take the point of that hook and put it down in about a 150-foot long area by 10 feet. And that's it. And you're moving at 150 miles an hour in a 54,000-pound jet, trying to land on a 98,000-ton ship that's moving away from you at 30 knots, and there's 25 knots of wind. That's about a 10-degree crosswind moving you off that center line. And there's so many different variables, it's mind-boggling.
So it's hard to be accurate. You don't see these guys executing those stunts while they're trying to land on this thing. I mean, this is something that if something goes wrong, it can claim lives. So it's very hard to do. So just to sort of summarize, you know, so yeah, before I get into that, so you know, this is actually a really important video. So you saw the video that I showed you in the beginning, and that's this amazing fighter pilot executing these just crazy stunts. But it's hard to be accurate, like landing on an aircraft carrier. When I watch this next video, I want you to pay attention and sort of see what is it about this video that makes it impressive. And this is sort of one of the world's best stunt pilots. Going fast and being accurate. So I say, you know, if those fighter jets are beyond the limit, this is certainly way far beyond the limit in terms of control. And these guys actually do this stuff in the wild, so it's not just a setup experiment. You see them sort of weaving through trees, avoiding these collisions by tucking in their wings and changing the angle of attack. This is actually a video that's not sped up, so it's a camera attached to a hawk that's weaving through the forest. And sort of this whole time is sort of weaving through there, avoiding, you know, sort of coming within inches of crashing at a pretty alarming rate, but he does this without a problem. And, you know, of course, they're accurate to pick the fish right out of the water. So, you know, for them, being fast and accurate isn't a problem. So, you know, the music definitely helps, I think. So just to summarize, you know, it's the state-of-the-art aircraft. They can execute highly dynamic and agile maneuvers, highly accurate maneuvers with some, you know, with quite a bit of effort, like landing on a carrier. But when it comes to combining those two, especially at low speeds for landing, it just doesn't happen. I'd like to say, and also that, you know, want to point out that they sustain a thrust-to-weight ratio that's greater than 1. And most birds just can't do that. So the whole thing is that birds are certainly one of the world's best stunt pilots. And so why is it hard? Why is this whole thing sort of not addressed by any of the control systems, or why is it hard for them to address this? And that's, so this is the Aero 101 slide. You have a wing on a wind tunnel, so you can see the stream of air sort of, you know, going over and under the wing there. As you start to tilt this wing, you increase the angle of attack, and that's the relative angle between the air and the actual wing. And you can see that the air starts to curve over the wing. There's a critical point when you go beyond this certain angle of attack. The air just can't curve around anymore. At that point, it detaches, it sort of comes and starts rotating behind the wing. And it causes this very turbulent, low-pressure region that is very hard to reason about. It's very hard to actually write down, you know, a closed loop, a closed form equation that will describe the behavior here. And so classical control systems just don't reason about this kind of thing. But you know, birds are always sort of certainly operating within this regime. They're sort of flaring their wings, sort of, you know, using that to stop and being able to, you know, land on the trainer's arm. And this is sort of another really impressive. So this is shot at 1,000 frames per second. This is a Eurasian eagle owl. But I want you to sort of just look at the ruffling of the feathers as this guy, you know, comes into land. And you can certainly imagine how complicated that airflow would look like if we were to visualize it. But again, has no problem coming in at a pretty significant fast speed and using the drag produced by his wings to slow him down and stop. So why perching? Like I said, we sort of fell in love with this maneuver that we thought captured a lot of the characteristics. So there's three things that we want to be able to compete with birds, and that's metrics of agility, accuracy, and maneuvering power efficiency. And so dynamic perching with a glider is pretty demanding in terms of all three of these. And so that's where we wanted the challenge. And and of course, one of the important things is that it requires us to reason about it basically requires us to operate it within this region of very complicated airflow. So, and this is another one of the challenges that we wanted to just go, head on. So I want to take a minute and just, point out that there's other perching work going on. So one of the related projects is going on here in John Howe's lab at the Aerospace Control Lab at MIT here, and they use basically a propeller pop hang to do the perch. There's another project going on at Cornell. What they do is they basically morph the airplane in order to be able to land. What they do is they morph the body up, they keep the wings level to keep that air very sort of attached and nicely behaved, and then you can sort of use these classical control techniques to be able to execute the perching maneuver. So this guy actually hasn't, they've done some simulation work, but they actually haven't gotten it to work on the real system, but I think it's progressing. There's another related project going on at Stanford, and they sort of look at mechanically how they can modify the glider in order to expand or increase the success rate of being able to attach yourself to a wall. So it's sort of, they brought one of these, they do this by designing a set of talons that they basically can stick to vertical surfaces. They brought one over, we put it on a plane, and it looks something like this. Oops, sorry. So it basically uses these talons to just hook onto the wall. And so the control here is actually very simple. You sense how far you are from the wall. At some point, you're close enough, you kick up your elevator, and you rely on the impact to basically attach to the wall. So what we want to be able to do is sort of land on a dime. And in that sense, it requires a little bit more thinking about the control. So we talk about we want to be able to compete with birds in these metrics. It's actually really hard. It's easy to say, but hard to quantify. So we started, trying to take a crack at trying to basically quantify how we perform versus a bird or a plane or a large plane. So we sort of came up with this dimensionless metric for avian stopping. And this says you can take a bird or a plane with mass M, wing area S, and an operating in a fluid of density rho. And it requires some distance x to stop from an initial velocity v naught to some final velocity. We define the distance average drag coefficient to be this expression. What this basically means is this represents the ratio of the distance that you would get for a flat plate at 90 degrees, the stopping distance that it would get, and versus what you would get on your aircraft. So you basically relate this to how the best performance a flat plate would be able to get for stopping distance. And what this translates to sort of at a high level, it's impressive to be heavy, operated in a low density fluid, have a small wing area, or stop in a short distance. Any one of these factors will sort of contribute to kicking this number up. And the higher this number, the better it is. So we started looking at some very preliminary reference numbers here. So if you look at 747 landing on an aircraft, landing on a runway, you get a distance average drag coefficient of about 0.16. The X31 Fighter Jet, which is sort of the state-of-the-art in high angle of attack landings, gets a number of about 0.3. And the Cornell perching plane that I showed you a bit ago gets a 0.25. And so the common pigeon, what would you expect for that to get? So it turns out that pigeons are actually one of the best perching birds. I was thinking of more like a falcon or something that would be way cooler, but it turns out pigeons are pretty amazing. They get a 10. So they're kicking our butts by so much, right? We have to be there. So that's where we sort of want to try to push the envelope. So one of the things that I said in the beginning, it's that we really had a hard time with was finding the right experiment. So what experiment could we sort of study to really allow us to pull out those fundamental principles about maneuvering flight and high angle of attack flight? And so we decided to go with perching So we wanted to go, and it was really important to isolate the flight control problem. So bring it in a lab and do things in still air with off-board sensing and computation. And so even though you're in a lab in still air, when you go into this high angle of attack, there's still a lot of stall and turbulent airflow that happens as this guy is executing the perching maneuver. So just because there's no wind gust doesn't mean it's simple aerodynamics going on. So it's still very complicated. And also we wanted to stick with a simple design. So basically what we did is just took one of those aerobatic planes that you buy from Hobby Lobby and scaled it down and say just made out of thin flat plates, and we're going to start with a simple design, find the limitations of the control, and modify it only if we need to. So the experiment looks like this. So that's the glider. It's about an 80-gram glider. It's got motion capture markers on there. There's some components of battery which powers the motor of the tail, so we can control the movement of that tail. So that's our actually only control input there. And we have a motion capture arena with 16 cameras. So this is only a sort of a cartoon that's showing 3, but there's 16 cameras tracking the position orientation of both the glider and the actual elevator. And the control loop looks like this. So basically you have your glider. The markers get picked up by the camera. The camera sends that information to the Vicon data station. This reconstructs position orientations and sends it out to the ground control station running MATLAB in C. So this takes all that state information, computes a controller through a buddy box interface through a wire, sends it to the transmitter, and this wirelessly transmits it to the airplane, and sort of this goes round and round. And this happens at about at about 45 hertz. The control loop happens at about 45 hertz. This state relay information happens at about 120 hertz. So the basic description of the perching maneuver is this. So this is sort of a cartoon. We initiate the maneuver at 7 meters a second, which is about 60 miles an hour, 3.5 meters away from the perch. And these are sort of limitations that are imposed by our capture space and sort of the bandwidth of the motion capture system. The glider has to come to a point landing in a fraction of a second. And since we don't have any onboard propeller, we claim that the only way to really do that is to stall the wings and use that as a brake to be able to minimize your speed when you land. So our flight arena looks like this. So I actually went out to Michael's and bought a big fish net that apparently still smelled like fish. I guess it was a used one. It was weird. I don't know why, but it was pretty cheap. And we did put this down just so we didn't have to rebuild the plane every single time it crashed, which turns out happens a lot. Flight projects are a pain in the butt, I realize. So this is what it looks like. This is the actual motion capture room. And if you talk to any control engineer, they tell you it's always useful to know as much about the physics of the system as possible, even if they're very complicated. So what we did is we said, okay, let's try to come up with a simple model. And this is sort of one of the simplest models for the glider that you could come up with. So it's 2 flat plates, one for the wings and one for the tail. And we can sort of reason about where the aerodynamic forces act for a flat plate. They're assumed to act at the center, perpendicular to the plate. We don't know what those magnitudes are, but we know where they act in their direction. We can measure lengths, we can measure masses and inertia, and use these to come up with a simple model. So now the question is, how do we get the aerodynamics? So what we ended up doing is basically shooting this airplane off about 220 times in this motion capture arena. Every time I would shoot it off, I would deflect the elevator slightly differently. Every time it would sweep out a little bit different portion of that state space. And the idea was to sort of gather all this information. So this is what it was doing. At first it would fly straight, then I would sort of, but little by little, deflect the elevator in a different way. You can start seeing this. You start deflecting, it starts executing some kind of different trajectory. And so we just basically kept all this data and try to characterize the aerodynamics. And so when we crunched the numbers, we were actually pretty surprised to find that they were as clean as they were. So what we actually did here is, so these are textbook equations, Aero 101 equations that tell you what lift and drag are. What we did is we basically computed these instantaneous values. So at every point, we know the glider is subject to gravitational and aerodynamic forces. We know what the gravity forces are, so the rest must be aerodynamic. That's what we use for the force term in there. The rest of these values are known, and we can pull out these lift and drag coefficients. So what these plots show is the lift as a function of angle of attack for the lift and drag here. And the blue is the actual data that we got that was actually, like I said, really surprising that it was as clean as it was, given that it was motion capture data. The red is what you see that's predicted by flat plate theory. So it turns out we were also surprised that even though the glider was made out of flat plates, as a whole it behaved as a flat plate. Now I do want to point out there's quite a bit of variance here on the drag coefficient here. I'm going to get back to that a little bit later, but I sort of just want to make you aware that there's something going on there. So, so now that we sort of got the final component of this model, the next thing is to try to design this control system. So we described the state of the glider. It's a 7-dimensional state, and it's translational positions here. You have pitch, theta, phi is the elevator angle, 3 derivatives. The 4th derivative is the actual input, so we can control the elevator velocity. So that's the state description and the input. And what we wanted to do now is design a trajectory using this model. So we basically formulated this as optimal control with a quadratic cost function problem. So we have a penalty on actuation, which is the R term here, and a penalty on final position, that's the distance from the perch. And we sum this over a finite time horizon. And the idea is basically to solve for the optimal U here. So we can sort of crunch through the optimization, and we get a trajectory in simulation using our model that looks something like this. So it looks pretty reasonable. We launch at our nominal initial condition, we come in, and the goal is to get that green dot, which is a hook, onto that black dot, which is a perch. So now the question is, what happens when we put this on the real plane? Because the simulation looks perfect, of course. So what you're going to see here is this sort of the same thing you saw in the beginning, that this is for the open loop trajectory that was computed. So the glider comes in. At this point, it's executing that computed trajectory that it got in simulation. It kicks up. The angle of attack is already really, really high compared to what we saw in the simulation, and it totally misses. So, I mean, it wasn't too surprising that this happened. Why? Because, well, one of the reasons is that we were only using an approximate model. And, when we put this on the real plane, there's certain dynamics that that weren't accounted for that do have some kind of effect on the actual glider dynamics. And so, it's not too surprising that that happened. So the next step that we wanted to take is how can we actually, compensate for these small disturbances and errors. And that's designing a feedback control system. So we wanted to compensate for model errors and reject disturbances. So we don't, in this case, we don't explicitly account for model errors. We just assume they're disturbances to the trajectory. And we formulate this as a linear time varying optimal control problem. We basically, the idea is that we have a nominal solution we have for that trajectory that we computed in open loop. So we know about what that perching trajectory should look like. And now the idea is that we're going to sort of use that as a guess, and then try to push the airplane as it's flying along onto this trajectory. So we linearize the dynamics about this nominal solution, and then we design a time-varying LQR controller, which consists of the nominal solution, which we computed before, and this is sort of the real-time error. So this is what's going to drive the glider back to the goal, and this time-varying optimal game matrix. So the name of the game is to find this K. And so this is a fairly well-formulated problem that we can also solve. Now, the picture here is that, like I said, we have a nominal solution, which is represented by the red line here. So, in simulation, we can sort of compute approximately what that nominal solution is. And then the idea with the feedback controller is to give this some leeway around that nominal solution. So the feedback controller was sort of, try to guarantee that any state within this blue region will be guaranteed to get back to the goal. So even if we deviate outside of this nominal solution, the error will try to drive us back. So, so if we implement this on the actual glider, this is what we get. So we shoot it off, and at this point, your feedback controllers, executing at about 45 hertz, you already see that the angle of attack is not as great as it was before, and it gets a little bit higher, makes it a little bit further to actually, that hook is probably a couple centimeters off from where the actual perch was. So, it turned out that fairly principled tools in optimal control were good enough to stabilize this maneuver, even though we didn't explicitly account for modeling errors. So going back to our performance against birds, so it turns out we get a 1.1. So it's not a 10, but it's definitely in the right direction. So there's two main contributors. So we want to sort of look at the robustness of this control system. And there's two main contributors, I think, that sort of characterize that. One is our ability to compensate for these disturbances. So it's, being able to compensate for disturbances is important when you actually start to go outside. You have wind gusts and all these other things. And the other one is the fidelity of the model that's used to design the control system. So the worse your approximation is of that model, the more far off your controller is going to be from what it should be. So these two things are sort of the major contributing factors. So let's look first at robustness against disturbances. So one of the most natural things to think about when you're thinking about how well I can control this glider is as the airspeed goes to 0, you have less control authority, which means there's less air flowing over your control surface. So that means you can actually generate less moments on your airplane. And so to try to quantify this, this notion of how well can I control the glider. Formally, the linearized system is controllable if you do controllability analysis. But there's there's complicated things going on that really makes us want to think about the problem a little bit more. There's 7 states in one control input. There's weak coupling, like I said, especially as you get down to the perch and your airspeed goes to 0. And there's some state-dependent sign changes between the relationship in the input and in the system response. And I'll make that a little bit clear. So there's some complicated things. So one of the natural questions to ask is, how well can we hope to control this glider in practice? When we actually start to get disturbances, how well is the control system going to be able to deal with this? So one of the first things that we looked at is this whole notion of instantaneous control authority. So if we consider the standard, and in any aircraft, the standard control inputs as being the control surfaces, elevator, rudder, ailerons, then the typical thing is to look at the aircraft dynamics on 2 time scales, and that's one that the dynamics of those state variables that evolve quickly, and the other ones are state variables that evolve slower. And so through standard aircraft control inputs, the ones that evolve quickly are the ones that are pretty much directly related. So like pitch rate, roll rate, directly related to elevator input and aileron input. The slower dynamics are the ones that you don't have direct influence on, like angle of attack and climb rate. So there's sort of the separation of time scales. For our glider, the one we can directly influence with the elevator is the pitch rate, and the slower dynamics are pretty much the rest of the state variables. So the question is, as the airspeed goes to 0, how does our ability to influence, the main proxy variable through which we influence the rest, how does that change? So this plot basically illustrates sort of the relative ability to influence pitch rate through the accelerations, through the moments. And you can see that as you get closer to the perch, the magnitude of this gradient decreases, it diminishes. And there's one actually interesting thing that happens up here, and that's that this gradient actually flips sides. So what this tells you is that a further deflection in the same direction is actually going to cause an opposite effect. So to sort of try to understand that a little bit, we can think of a glider. Think of a glider in steady level flight. And in steady level flight, what we're going to do is vary the elevator angle from 100 degrees to, or negative 100 degrees to 100 degrees, and see how we can change the moments generated by this glider. So what this curve, there's 2 things that I want to show you here, and one is how your ability to generate a moment decreases as your airspeed goes to 0, and the other one is the sign change that I showed you a little bit before. So basically what these curves represent, so on the x-axis is the actual elevator, So in that picture that I showed just right before, we're going to start moving this elevator forward and backward, and that represents this axis. And this is the actual torque that is generated. So the biggest curve is the torque that is generated for the largest velocity, 7 meters per second. As that velocity is decreased, the magnitude of this curve has an inverse square relationship with the velocity. So it drops off until it gets at 1 meter per second, which is about the same order that we are right before we land. We can deflect the elevator as far as we want. The magnitude that's going to be generated for that torque is almost zero throughout the whole range here. And the interesting thing is that at zero angle of attack, you would expect that there's no moment. There's two other points on the extreme here, and what happens is when you're transitioning from one of these zero moment points to the other, the curve sort of hits a peak, and at that point, it sort of starts to go down, and these correspond to the moment arm for the force on the elevator being zero, and that is basically this case. There's a certain, for our case, it's 94.67 degrees, which will depend on the distance between the hinge and where the force acts. But at this point, the force is perpendicular to the line of action. So there's absolutely no torque being generated here. And so that's what these two extreme points represent. And so the transition between that causes that gradient to hit zero. So, going back to so now that we see and we can sort of visualize that our instantaneous control authority goes to zero as that speed decreases, how does that affect our ability to actually reject disturbances? So we actually started looking at the most natural disturbance, and that's just a wind gust disturbance. That was sort of the first thing to look at. So what we did is we basically, at every control input along that trajectory, we basically added a perturbation to the wind, both the wing and the elevator, unit perturbation. And what we did is we propagated one step forward. And so now that we added this disturbance, we propagate one step forward. And what is going to happen is when we propagate one step forward, we're going to get a new state that is slightly perturbed from what it would have been if we had no disturbance. And what we do is evaluate, assuming at that point we follow the optimal policy, we can evaluate what it would cost, what that perturbation costs in terms of an optimal control sense. So this is your perturbed state, your state that you would have gotten with no perturbation. S defines your optimal cost to go. We can evaluate that. So just really quickly, again, you can see that the instantaneous control authority goes to zero. So you would expect, presumably on first look, that as you get closer to the perch, if you get a wind gust, it's going to kill you. So the cost would be really high. But it turns out, actually, that it's not quite that easy. So what happens is actually, towards the beginning and at the end, it's fairly insensitive to wind gusts. So the intuition behind this is that at the beginning you have sort of sufficient time to correct for the wind gust. So that sort of makes sense. At the end, if you remember, there was this separation that I talked about in timescales between the dynamics evolving to other state variables. So even though you have a wind gust here, it sort of affects your pitch more instantaneously, more than anything else. And it does that pitch. You sort of change a pitch, but it doesn't have enough time to integrate to a substantial position error. And the position error is the one that has the highest cost, right? So this is pretty, characteristic of the cost function that we chose. And if we look at the optimal controller and that cost that we assign at the end, we assign 100 to X and Z. So to the positions we assign 100. This is our penalty on being away from that perch. And pitch and velocities are relatively small. So this is sort of a consequence of how we define our cost function. But even then, for this perching control system, it's fairly interesting to see that it's not very sensitive to these wind gusts. And sort of in the middle is that critical region where these. Yeah, John.
How did you choose the direction of that wind gust? Is the arrow indicating?
Yeah. So I was actually just gonna tell you about that. So the way that I did this, at every control DT, I basically hit that unit perturbation, and I did a line search for the worst possible angle of that wind gust, and that represents the worst possible angle along the trajectory. So this is sort of the worst unit wind gust that I could have gotten, and that's how I used to evaluate this. So So the point here is that although the instantaneous control authority diminishes as we approach the goal, that the sensitivity to wind gusts is actually not affected, that much. And that was pretty surprising to find. But that means that this instantaneous control authority isn't important, because certainly when you think about sensors, when you get to the perch, there could be a huge jump in position, for example, and your ability to instantaneously control yourself is actually going to play a pretty important role. So this is not something that we're considering right now. So so I just said that. So so the other part of it that we wanted to look at is in terms of robustness is how robust is this control system to initial launching speed. So we solved for 7 meters per second, and then we let the control system basically compensate for any changes. So this is sort of what we get. So the nominal, so this is plotting initial forward speed versus the final distance to the perch. So we can see that, and this is all in simulation. The nominal trajectory was solved for 7 meters per second. So naturally, the blue here is the open loop, the red is the time variant LQR. So naturally, at 7 meters per second, the open loop will have no problem. And as you start to deviate away from that, you're going to start incur errors in the final error. So the LTV, or sorry, the TV LQR control system actually slaps these errors locally around this nominal solution down to 0. And as you start to get away from the linearization, you start to incur more cost, because at that point your approximation of the dynamics is not correct. What we want to do, ideally, is get all these points down to 0. So we want to slap all these red points down to the 0 axis. That's sort of the goal. So the way we can think about this is trajectory libraries. So we took the approach of using LQR trees. And the idea is this, is that we have a nominal solution that we compute, open loop nominal solution. We compute this time variant LQR controller, which gives us some basin of attraction. And now what we're going to do here is reason about the width of that basin of attraction. This is an approximated basin too, I want to point that out. And then we can sort of characterize the width of this basin of attraction by this parameter phi. And it's a time variant, so as this thing flies along, at every point, the width is going to change. And this, just to make it easier on myself for drawing, the width is the same, but you can imagine this changing. And what happens is this blue region will represent all the states of the linearized system, such that the cost to go to stabilize that state is going to be less than this parameter phi. So any states that are within this bound on your cost to go are going to be considered to be in the basin of attraction, rather than in this region of attraction. And J here is represented by the standard cost to go, linear cost to go here. So the question is once we have a glider position that's outside this basin, how do we actually get it to stabilize it? So one thing is to ask, first thing is, as this algorithm is crunching along, and ask, is this in the existing basins? If it looks at the current tree, in this case it's just one, but it looks at the current tree and asks, am I in the blue region? If not, then what it does is plan a trajectory back to the tree, or potentially back to the goal, and computes its own basin of attraction. And it sort of keeps doing this, every time it keeps sampling, and the sampling, you can actually prove formally as the sampling goes to infinity that you will actually cover the entire state space with these blue regions. So basically, any point in that state space within the bounded, that is capable of getting to the goal will get to the goal. So eventually you start doing this enough, and you start seeing this tree structure, hence the name, the LQI trees. So geometrically, you can sort of visualize as a funnel, and if you think of the XY plane here representing our state space, and the controller being represented by these funnels, you're at some point in state space, and when you project up, the controller actually sort of funnels you down to the mouth of the next funnel, and eventually gets you down to the goal. So you're sort of like switching between controllers until you get to the goal there. So perching with LQR tree. So now I'm going to show you here is that same simulation, but now we're going to vary the initial speed from 6.5 meters per second all the way to 9. And you can see that it's actually pretty robust to these initial condition changes in speed. So every time it sort of behaves a little bit differently. Kicking the elevator a little bit harder just to sort of be able to stop even though you're sort of going faster. So going back to this plot, so this is the original plot that we had for the single time varying LQR controller. When we have the LQR trees, we can see that we can pretty reasonably slap a lot of those errors almost down to 0, except for the extreme here. What happens here is there's just not enough energy for the glider to get there. So at 6 meters per second, it's pretty much, you just not fast enough to get to the perch, which is 3.5 meters away. Yeah.
On the right note, there's slightly lower speed. So the LQR3 seems to be doing worse than the original.
Oh yeah, so and I'll show you this actually. Oh sorry. So it doesn't solve the nominal. So when I did this sampling, I didn't solve for the nominal anymore. I solved it for somewhere else. And so this is all based on sampling. What the nominal was, probably not at 7 meters per second. So these colors represent the different branches now. And it was probably somewhere over here. I didn't simulate it out, probably anywhere around here, which is why it's not 0. So that's the reason. But you can sort of see that with a few number of branches, you can actually cover and slap a lot of these down to 0. So just to give you a visual of what this looks like, comparing the LQR tree solution versus the open loop. So 9 meters per second, we're going to launch this thing in simulation. Open loop does something like this. And we do the LQR trees feedback stabilizing, and we get something like this. And on the other extreme, almost too slow not to make it, open loop solution does something like this, so it just barely misses it. And you can see that the LQR tree solution will just make that extra effort just to barely get there. So this is sort of at the boundaries. You start decreasing this, you're just not going to have enough speed to get there. So I said there was sort of 2 important things that contributed to the performance of the control system. One is disturbances, being able to compensate for disturbances. The other one was with modeling. So we actually are trying to understand the modeling as well to get higher fidelity models to design our control systems around. So if you remember, I pointed out the large variation in the drag coefficient. So it turns out if you plot one of the trajectories that I shot off the plane over time, you're going to see an oscillation in the drag coefficient here. And if you sort of figure out what that frequency is, it sort of lies somewhere around the 11 hertz range. So if you do a sort of a back of the envelope calculation for a vortex shedding off a flat plate, it sort of lies within that same region. So it's it was certainly plausible for us to think that we were actually seeing some artifacts of vortex shedding. Now, we wanted to sort of verify, so we took a page from the Fluid Dynamics experimental handbook, and we designed this experiment. And this is basically a laser, which through some optics gives you a planar sheet, and you generate smoke from the leading edge. And the hope is that we can throw this thing and start to see what the air looks like, and look at the frequency of this vortex street and see if that sort of matches what we were seeing in the data. So basically, so Ron Wicken, sitting over there, the man, helped me build this huge wind tunnel from Home Depot parts. So it's about 18 feet long, 6 foot across, 6 foot high, or 4 feet high. It's got Lasco box fans for $20 or something from online. It's got a huge honeycomb here, mixing section, exhaust section, and it's got a window here, so we can launch the glider here and start to visualize what the air looks like. And this is actually what it looks like. It's building N10 now over by the aero department, but it's not very high tech, but it works for what we need it to work. And when we actually start shooting this thing out, we start to get these beautiful pictures of what the air looks like right behind the airplane here. So you can start to see, even though they're a little bit cloudy, that there's certainly a structure to this vortex wake. And it turns out, here's another picture here. It turns out that the frequency of these this vortex street actually is on the range from 11 to 14 hertz. but it's pretty close to what we were seeing in the data. So David Lentic, who's looked at this for his master's thesis, he's on my committee on the other end of the world right now. But he started to plot, make these beautiful plots of what you would get if you, so this is drag coefficient and lift coefficient for a flat plate at, so it's a polar plot for varying angles of attack. And so this is the steady limit cycles for the vortex street oscillations in lift and drag that you get. So after you hit this, get to this angle of attack, the air stabilizes. You get oscillations in the lift and drag forces, and these oscillations are sort of characterized by these loops here. And it turns out that the frequency of these loops can be described by what's called the Struhal number. But if we look at one of these curves here at about 45-degree angle of attack, these bumps actually correspond to when these vortices are shedding off the leading and trailing edge here. So one of the cool things about this is that people who have been doing walking have been looking at limit cycles for a long time, and trying to understand how to stabilize limit cycles is something that they've done a fair share of work on, and so we're sort of excited about being able to apply those same things in this domain. So trying to basically use some of these models to try not only to get a better understanding of the physics, but to see if it's actually important to model these effects when we're trying to design a robust control system. So one of the things that we wanted to do is, like I said in the beginning, is understand and try to be as graceful as a real bird. So there's a certain advantage, I think, to having flapping wings that can move. And just like a human that can manipulate its objects, with its hands or with its fingers, I think birds sort of have that same capability. They use the wings to manipulate the air around them. And so we wanted to sort of try to understand what the consequences of having flapping wings are. So we think there's two important things. One is potentially increase that instantaneous control authority. So as you're flapping your wings, even though your body airspeed is near and zero, you can flap the wings and generate a velocity over the wing to keep a certain amount of control authority right before you land. And the other one is you can actually stop faster. So as you're coming along, you can actually flap forward, and since the difference in speed is the force is quadratic and the difference in speed, then you can actually generate a higher force. So this is basically a little toy. We said the simplest thing we could possibly do is actuate the wings on the glider. And so basically we wanted to try to understand the next sort of baby step towards mimicking bird flight. And so just like the glider, we can write down the equations. There's extra terms because of the moving of the wings and integrals over the wing itself. But sort of we can jot these down if we simulate it. So this is an open loop controller that is using flapping wings. Sort of, it's really slowed down. So that whole thing was about a second. So what I want you to notice is that right before it lands, that flap that it gives sort of almost makes it stop in midair right before it comes down. So the next step is to try to build something like that. So this is our best efforts to try to build a flapping wing airplane. Well, at least my best efforts. There's probably better people to be able to do this. But we put a transmission just in the belly of the glider. And this, basically flaps the wings. It's just one single degree of freedom. So we can control the flapping rate. We can't control the position. We have a little battery and whatnot. And we have, the same motor at the tail. And so we start flapping this thing. So I think one of the most impressive things about this is that it's made out of foam. And it's impressive how fast this thing goes without breaking. I totally thought it was going to break at some point, but or just launch off the rail or something. So I totally thought it was going to break, and it didn't. I mean, I could have had a more elegant ending to that video, I guess. But so it actually worked, and So the next thing is I was so excited I wanted to put this on and try an open loop controller to see what would happen when this thing started flapping its wings right before it landed on that string. And I want you to look at this and you sort of remember the simulation that you saw, that it's sort of there's this extra stop that you get by flapping the wings, and I think you'll be able to see at least something that looks. So even though it's not as pronounced, this thing comes in, it starts flapping its wings, and right here, you see that it actually, gets that extra break right before it lands. So there's definitely something that allows you to kick up your braking abilities, and that's one of the things that we wanted to look at. So in parallel to all of this, while we were working, there's a whole bunch of students helping out to also look at the extensions to flapping wings. So we started buying some robot birds to build plans to build a robot bird, and we started playing around with these things, started getting some high-speed video, because these birds actually fly pretty well. I mean, and they were designed by some guy in his garage, trial and error, but he just did it right. And it's amazing how beautiful these dynamics of these flexible wings are. And we built our first one, so I think you see John Jock's head at some point here. You were there. This is sort of the first successful flight, killing Cory. So, it's amazingly bird-like. But you ask the pilot, and he'll tell you that it's to try to control this thing the response is a lot more sluggish than any other, aerobatic airplane. So it hits the tree, and he's able to catch it. So this is all pilot control. And this is basically just testing the mechanical design. So we took this design and scaled it up to be able to carry a computer on board. So this is work by Zach Jakowski in our lab, and he basically has a titanium wielded gearbox here, the same sort of design, but he's carrying a Linux computer on board with gyros, accelerometers, a sonar sensor, and this is pictures from Jason Dorfman. This is in flight. And this is the first autonomous flight that it took. So we wanted to see, now that we have a full computer on this thing, can it fly by itself? Just steady level flight. And so this is our first success here. So we sort of launch it off. This is all computer control at this point, but it's about to hit the building, so we shut it off. And that's how we get rest and do exercise. We haven't chased the robots all the time. So where are we going with this now? Joe Moore in our lab is already starting to instrument a glider with a computer on board, accelerometers, gyros, and a magnetic field sensor to be able to go outside, sense the magnetic field on a power line, and land on the power line itself. So we're pretty excited about that. We're also thinking about feedback control for the flapping perching. So trying to come up with a control system that can exploit this capability of being able to stop quicker and potentially increase your control authority. We're also excited, to work with David on actually looking at real birds. He's actually been putting birds in a wind tunnel, and we're talking about putting them in motion capture, and try to understand, maybe the kinematics and just really the fundamental principles behind bird landing, and try to use that in the design and the control. And also, as these things get more complicated and our models get, our model approximations get worse, is there any advantage to using learning control, that is allowing the control system to tune its own parameters online on the real robot? So this is something that we started to think about. So what I want you to go away with is, what I demonstrated is that even a kinematically simple representation of a bird, that's a simple fixed wing glider, can robustly execute an avian-like perching maneuver. It has only a single motor at the tail, and it's stalled wings and control surface, but it's still able to robustly do this. And I want to make a point that even though aerodynamic mechanisms on birds may play an important role in these types of maneuvers, they're really hard to quantify and understand. But I think by most measures, we do pretty well with a fixed wing glider. And in spite of these complex aerodynamics, these approximate models are sufficient for good control. The catchphrase that's always thrown around our lab is that birds don't solve Navier-Stokes. So it's highly unlikely they have a full representation of the unsteady fluid dynamics that are going on, but they have some approximate model. And so, we also showed an indicator in that video that flapping wings can increase your braking ability and potentially your control authority, and that's something that we're actually interested in looking at. And the last point I want to make is that optimal control in these frameworks are really a powerful tool for solving highly underactuated control problems. And I mean, in these sort of generalized, not only to flying, but in our lab, in particular, we're doing this for walking. And you can certainly imagine domains where this stuff would extend as well. So one thing that I want to point out is that, I was really excited about looking at birds for inspiration, but it's really important to keep in mind that you don't want to mimic. You want to get inspiration from these birds because they're not perfect. So, for example, have you ever seen a bird miss the branch? Or actually, not calibrate too well. Look at this guy. Bread in the water, right? So these guys aren't perfect. But he's okay. So I just want to thank everybody that was involved in this and the work in this thesis. There was so many people involved, and everybody made my life awesome and really enjoyable. Everybody in my group. So I want to give them a huge thanks. And that's it.